Hi guys, so this is it. We're down to the wire, our very last unit, Unit 4, statistics. So the first thing I put together for you is a little review with notes. We covered the central tendencies or types of averages, which include mean, median, and mode. Mean is the one where you add the values and divide by the total quantity of values. Mode means most. So if you're looking at the histogram, the highest line, the highest bar would contain the most. And median is the middle when the data values are in order least to greatest. And it's nice that Excel can do that for you. Next, we looked at the box and whisker plot. Box and whisker plot is a great way to represent data because the data is represented into four segments, each segment representing a quartile, which means 25% of your data values, and it goes above a number line. So it's easy to read what the values are. I like what's called the 5-number summary down here. And the 5-number summary, I always start with the lowest value and the highest value, and then I get the median when all the data are in order. The lowest value I plot on the number line where it belongs. The highest value I plot on the number line where it belongs, and the median. Then I get the lower quartile and the upper quartile. The lower quartile are the bottom half of your data. So if you have 14 pieces of data, you would have 7 on the bottom half, 7 on the top. The lower quartile will be the exact middle of that bottom 7. So the fourth piece of data would be the lower quartile or Q1. If you have 7 data values on the top half of the other 14, then it's the fourth over. So it's like the 11th value. So it's the middle of those 7, the fourth over or fourth from the end, and that would be your upper quartile. So here's a picture. I'll move it up a little so you can see it better. Annual cost of college. This particular one also included the mean. You should be able to tell that the mean is higher than the median on this because this middle box always represents 50% of the data values. This tail, this whisker from the bottom to the beginning of the box is the lowest 25%. Then from this dot to the middle dot, which is your median, this 25% is clustered very, very closely together. Then the next 25%, you can see how wide this is spread out. This 25% is more spread out. So because this is wider than the bottom half, it would mean that the mean has to be higher than the median. And then the upper quartile is way up here. This particular one wrote the values on, but usually you would just go straight down to the number line to read the values. So 25, 25, 25, 25, 50% right smack in the middle. This middle, the box always represents the interquartile range or 50% of the data. We did talk a little bit about confidence intervals after looking out at the normal distribution graph. The normal distribution graph will be a bell shape. So basically it's a histogram. When you plot all the points in a histogram, if it's a normal distribution or a near normal distribution, it will have a nice bell shape. So the confidence interval, if you know what your statistic is, one way to get your statistic is just by doing this. It's the number of successes over the total number. The statistic or the mean would go right smack in the middle. And then The green is representing one standard deviation. One standard deviation over, you'll see 1 SD. One standard deviation to the left is actually one below, so that would be the standard deviations or standard deviations. But when we talk about z-scores, these would be negative z-scores, anything to the left. Anything to the right would be positive. So 68% of the data will fall within one standard deviation. 95% of all data, 95, so that includes all the green and all the blue, will fall 95% of the data will fall within 2 standard deviations. 3 standard deviations, the end of the red, where the red ends, so it's everything in the red, the blue, and the green, is 99.7% of the data. You can have standard deviations 4, 5, 6 above and below. So the empirical rule is 68, 95, 99.7. So if you are required to use the empirical rule, remember 68, 1 standard deviation away. 95, 2 standard deviations away. 99.7, 3 standard deviations away. So I'm going to go back to this confidence interval. It is your statistic plus or minus your margin of error. So if we have a 95% confidence interval, it would include everything from the blue to the green. It would include 2 standard deviations below up to 2 standard deviations above. The rule of thumb is 95%, 2 standard deviations. So you'll see here, margin of error equals twice the standard deviation of your statistic. So you can subtract, you can use the 2D method, any way you want to use it. A bell-shaped histogram whereby the mean, the median, and the mode all equal each other and basically mirror each other is called a normal distribution. So notice 65% of the data values fall within 1 standard deviation, 95 fall within 2, and 99.7 fall within 3. Now, variability and standard deviation and how they are related. I think this has been a little bit tricky for some people. Variability means how far apart the data values are. So if the data values are really, really all over the place and they're very, very far apart, they have a high variability. If all the data values are all clustered around one point and they're all very, very close together, they have a strong variability, which is sort of related to standard deviation, because by definition, standard deviation is actually the average of every single statistic value, how far away each and every statistic value is from the mean. And then you get the average of all of those values, and that's your standard deviation. It's a long process to calculate by hand, but fortunately we get to use Excel. Before Excel, we used graphing calculators. So let's look at what this means. Standard deviation is a numerical value used to describe the variability of the data values. The smaller the standard deviation, the closer the values are clustered together. The larger the standard deviation, the more spread out the data values are. Standard deviation is the actual average of the distance of each of the data points from the mean. So from standard deviation, we can get a z-score. A z-score is applied to each and every data value. So you can look at every single data value and determine how far away from the mean it is. That z-score is going to give you a value that's going to say plus or minus some value. If it is less than 2 standard deviations, so if it's from anywhere from -2 to +2, anywhere from -2, let me go back to the picture, anywhere from -2 to +2, anything in here, anything in the blue and the green is considered within normal range. Any values in the tails, the right tail or the left tail, they are considered unusual. It may be unusually heavy. It may be unusually tall. Same with the low values. A person may be unusually short, or an object may be unusually heavy. So the z-score is an actual specific value that reference the mean. It can be positive or it can be negative, depending on what side of the mean. There's normal range again. Any data value within 2 standard deviations is considered within normal range. And that 2 standard deviations is from our mean. Any data value more than 2 standard deviations from the mean is considered unusual. You can have an unusually low value or an unusually large value. Since 95% of data values fall within 2 standard deviations of the mean, you can estimate the 95% confidence interval just by knowing the 2 values, the 2 standard deviations, the value that's 2 standard deviations below the mean and the value that's 2 standard deviations above the mean. That would give you an estimate. Your textbook also has a tool to calculate the confidence intervals and the margin of error. You just need to know the number in the sample, the mean, and the standard deviation. A 90% confidence interval, I skipped one. Confidence interval, what it is by definition. It is a range of values that is thought to contain the true population value, the true population mean. And there are 3 popular ones, 90%, 95%, and 99%. When you're doing a survey, it's unrealistic to survey billions of people. If we were to survey every single person in the world, we would have to survey billions of people. That would be the population. But we can make projections about a population from a sample. As long as the sample was randomly taken and the questions were not biased, we can use a sample to make a general conclusion about a population. So that's what statistics is really about. It's about using a representative sample, a sample that represents the population, and trying to use that value to come up with statements about the whole population. The margin of error is the distance from the sample mean to one end of the confidence interval and then to the other end of the confidence interval. So you only count the margin of error once. The difference from the low and the high is the range of the confidence interval. Right smack in the range of the confidence interval will be your statistic mean or your statistic. Well, the difference from the statistic to the end of the confidence interval, that is your margin of error. That's why the margin of error can be positive or it can be negative. So margin of error is the distance from the sample mean to one end of the confidence interval. There's that word confidence interval. If you know your statistic and you know your margin of error, you can determine the values for the confidence interval. You would take your statistic minus the margin of error, you have the low value. Take the statistic, add the margin of error, you have the high value. So another way to think of the margin of error is for the 95%, this works 2 times the standard deviation. Okay, how to determine the sample statistic when given the confidence interval. I think several people got stuck with this. This was homework 4, and it's why I put together the last video. So if you're trying to determine the statistic from the confidence interval, all you have to do is find that exact middle. There are a few ways to do it. Think of it as getting the average of those 2 endpoints. Add them together, divide by 2, and you'll get your statistic. Another way you can do it is to get the range of that confidence interval. The high value minus the low value is going to give you the range. Divide that in half, and again, you will have the sample statistic. Think about whatever way makes more sense to you. How to determine the margin of error given the confidence interval. Get the difference of the low value and the high value. Just get the difference, divide by 2. You now have your margin of error. How do you write the confidence interval using plus or minus? First, you need to know what the mean is, your sample mean. Then you simply put plus or minus your margin of error. So the confidence interval equals the mean plus or minus the confidence interval. Using Excel, you will have to use Excel for your Unit 4 quiz. You put your list in. That's the first thing. Just copy your list, go straight down with your list. Then in the cell where you want to put the mean, start with an equal sign. You cannot type the word mean. It will not work. Another name for mean is average. So you put your cursor in the cell where you want the mean to appear. Put the equal sign in. Type in the word average, and it'll come up before you even finish the whole word. A set of parentheses will open. Grab the top value of your list, right-click, drag it down to highlight the list, let it go on the bottom one, close the parentheses, hit enter. Excel will calculate the mean for you. Excel will also calculate the median for you. Do the same thing. Put your cursor in the cell where you want your median to appear. Click on the top value in your list, right-click, hold it down to highlighted, stop at the end of the last value that you're looking for, and let it go. Oh, I forgot to tell you, when you're doing the median, type in median. As soon as you put MEDI, the only word you will see is median. So click on it, double click it. A set of parentheses will open. Grab from the top of your list to the bottom of your list. Close parentheses, hit enter, and you will have the median. They don't even have to be in order least to greatest. Excel will do the work for you. Excel will also determine your sample deviation, your sample standard deviation. Everything that we are using is only a sample. We do not have the entire population. So for our purposes and for this course, you have your list in there. Find the cell where you want to put your standard deviation, hit equal, and as soon as you start typing STDEV, you're going to see two of these show up. One with a dot P, one with a dot S. You must choose the one that has S for sample. Even though we're going to make conclusions about a population, we only have a sampling. We don't have a whole population. So double click on the one that says STDEV.S. A set of parentheses will open. Go back to the top of the list, click it, drag it down to the last digit, let it go. The data will go into the parentheses, close the parentheses off, hit enter. You now have your standard deviation. So for the most part, that is a nutshell of every single thing we did in Unit 4. I'd like to do some practice questions to help you prepare for the quiz. It is the last quiz, and some of you are teetering between an A minus and an A, some between a B plus and an A minus. So it's really nice to get that little jump and get the highest score. So it says copy and paste the sample data below into Excel. You do not need to include the Excel file when you submit your quiz. Just give your answers in the spaces below. So here is a random sampling of some New York State teacher salaries. I did go look them up. I took the median salaries for a few places in Dutchess and Westchester County. You can easily tell which one came from Westchester, the 91,000. But the rest of these are from different school districts in Dutchess County. I just randomly clicked anywhere. It's not really a totally random sample in that I didn't use a program to make it random. I just blindly grabbed and copied. So to make this go a little bit shorter, I've taken this list and I've already posted it in Excel over here. Hopefully you can see it. So I did hit the money icon, so everything turned to money. First question, use Excel to find the mean. So I'm going to Excel. I already set up mean, median, and standard deviation. The only reason why I put these in a different color is so that I know where to stop my drag. So when I click on and drag the numbers, I don't want to accidentally go too far, so I put a color in it. So I'm going to start with the equal sign, and I have to type average, AVE, and you see the second one down, it says average. Double click it. It will automatically open parentheses. I click on the first one, hold it down, drag to the bottom one, let it go, close parentheses, hit enter. The next question is about the median. So I'm going to do the same thing. Start with an equal sign. I think I missed it. Sorry. Start with the equal sign. I start typing in median, and it immediately is the only one that shows up. Double click it. It will open parentheses. Click on the first one, hold, drag to the last one, let it go. Close the open parentheses, hit enter. One more to get through. Standard deviation. This is the one where you have to be careful. Hit equal, start with STDE, and you'll see there's a P and an S. We need the sample one. So I double click the sample, grab the top, pull it down to the bottom, close parentheses, hit enter. Now the homework and the quiz will say you do not have to copy and paste this over. I am going to go to the snipping tool just so I can show you that when I'm putting them over, I am in fact putting these values. So I'm just going to grab these three values here for a second, bring them over to my work, and hit Control V so I can see them. So the answer to the first one is $61,117.44. I want to make sure that my instructor can see it, so I've changed its color. My second one, the median, is $58,700.00. Again, I'm going to make it another color so my instructor can read it. Didn't really need to put those 2 zeros there. And the standard deviation is $12,683.80. And I am going to change the color to make it easy to see. So I'm going to leave this here for now, just squish it, move it out of the way a little bit, and bring this up. So it's interesting here because it looks like the average, the mean salary is about $61,000. The median is 58. This standard deviation of 12,000 could be 12,000 up or down. I bet if this 91,000, which is an outlier compared to everything else, was not here, the values here would be much closer and this would be smaller. But it's what we have. Now we have two box and whisker plots on one number line. The box plots below show the ages of two different counties in Florida. Use the box plot to answer the question. So we have County 1 and County 2. And when I look at County 1, the range seems to go from 0 up to 109. I look at County 2, it goes from 0 to 108. So there is not much difference in the range. But look at where the boxes fall themselves. So in County 1, the 50%, the middle 50% goes from 23 to 64. And the middle in County 2, the middle 50% goes from 15 to 43. That makes me think that on average, the people in County 1 are a bit older than the people in County 2, just because of the fact that 50% of County 1 is older than the last 25% of County 2. Remember, 25%, 25%, 25, and 25. 25, 25, 25, 25. So these two represent 50. This represents 25. Now, I haven't answered any questions. I just took a quick look at the box and whisker to get a feel for what they're trying to tell me. So question A says, Lila is a resident in County 2, and she is the median age. How old is Lila? So County 2 is the bottom one. She's the median age, which would be right smack the line in the middle of the box, which would make Lila 29 years old. Lila is 29 years old. And of course, I wrote it in a sentence, answered it, and highlighted it so the instructor can find it. Question B says, fill in the blank. Corinne lives in County 1 and she is 64 years old. This means that Corinne's age is higher than what percent of the people living in County 1? So here's Corinne's age. This is 25%. This second section is 25, and this is 25. So 25, 50, 75. She is older than 75%. And it says it has a spot for answer out here. So, and it just said fill in the blank. So I'm just going to write the 75%. I could put it in a sentence, but it looks like it would fit there. Actually, I'm going to do copy. Whoa. What did I do with it? Let me just hit back because I don't know where it went. Control C, put it on the little line, Control V, and now I've answered the question. Get rid of that little piece there. Oh boy, there's more questions, but now I can't see the line. Okay, it says Brian is 44 years old. Should say years old. There's an error, but I'll add the S, but it probably won't show on yours. Brian is 44 years old, living in County 1. This means he is older than what percent? So we're going to County 1, looking for 44. County 44 is the median. So what percentage is he older than? He's older than everybody below him. So that's 25 and 25. He's older than 50%. 50%. Again, make it a color so that my instructor can easily see it. And I will put it on the line, even though it didn't say I had to. Okay, Tony is a first quartile person in County 1, and Jose is a first quartile person in County 2. How old are each of them? So we're looking for Q1 in both counties. Tony lives in County 1, so let's go get his age. Q1 is 23. So Tony is 23 years old. Whoops, I went too far. Okay, and Jose, we need Q1 in County 2. He's just a teeny bopper. Jose is 15 years old. Make sure my instructor can read it. Okay, we're getting further down on here. This looks like a multiple part question. In 2004, the average LCD TV screen size was 25.4 inches. I did look up statistics on this to get these values for you. In 2004, the average LCD TV screen size was 25.4 inches with a standard deviation of 5.3 inches. In 2019, the average LCD TV screen size was 48 inches with a standard deviation of 4.2. Now, let's just take a quick look. Let's think about what's being said here. Okay, so in 2014, the screens were quite a lot smaller than they were in 2019. They went from just over 25 inches to 48 inches. They've almost doubled in size from 2004 to 2019. In 2004, the standard deviation was 5.3 inches. So there were people who had TVs that were about 5 inches or 10 inches. Well, I doubt 10 inches would be there, but we'll see. And then 5 times 2 is 10.6 inches tall over. That would give us our 2 standard deviations. So 25, 35, about 36. So that's what's happening here. In 2019, the average LCD TV screen, and this is what was sold. It wasn't necessarily that it was in houses, it was what was sold. So 48 inches, and the standard deviation is a little bit smaller. It's 4.2. So 48 minus about 4 would be 44. That's one standard deviation. To go 2 would be down to about 40. So these, 95% were from 40. 4 over 48 plus 4 is 52 plus 4 is 56. So this had a smaller range, but they were all larger. Okay. Identify which of the following statements is correct. I never like these because sometimes it could be more than one, but usually it's one. Let's find out. Since the standard deviation in 2004 TV is higher, well, that's true. It is higher than the other one. 2004 TVs have greater variety in screen size than 2019 TVs have, and 2019 TVs have more similar sizes. Well, based just on standard deviation, this seems to be true. So for now, I'm just going to highlight, I can't do that. Well, for now, I'm going to highlight this knowing that is true. If I'm wrong, I'll go back. Okay, oops, I want to be able to see the question. The standard deviation in 2004 TVs is higher. That's true. 2004 TVs have more similar screen sizes. That's not true because 2019 are not varied. These are closer. This is false. Okay, let's look at the next one. Since the mean of 2019 is higher, well, that's true. This TV has more similar sizes. Well, the mean average doesn't have anything to do with the variation. While 2019 TV screens are more varied. Well, part of this is true, but part of this is false. So that leaves that out. Let's go to the next one. Since the mean of 2019 TVs is higher, 2004 screens are more varied. Well, we're talking about mean and variation. This doesn't have anything to do with this, while the 2019 screens are more similar. So 2 parts true, 1 part false. The only one totally correct is the top one. Oh boy, another question. So let's just make sure we know what we're doing. This is a mean of 25.4, standard deviation 5.3. Mean of 48, standard deviation of 4.2. Since the standard deviation of 2004 screen is higher, that's true. 2004 screens that are larger on average, the 2004 screens were not larger than the 2019 screens. That's false. Since the standard deviation of 2004 screens is higher, that's true. The 2019 screens are, well, they are larger, but this does not cause this the standard deviation of 2004 being larger does not cause the 2019 TV screens to be larger. So this is nonsensical. Since the mean of the 2019 TVs is higher, 2019 TVs have larger screens on average. Well, they do have larger screens on average. They're 48 compared to that. So where was that? Since a higher, okay, let me highlight this one for now because I know this one is true. Since the 2019 TV size is higher, the 2014 screens are larger. Well, that's totally false. So there's 1 and 1. This had 1 that worked, this. Okay, moving on to the next question. Oh, more teacher salaries. Suppose that the teacher's salaries in one state are normally distributed with a mean of $907.33 on average. These must be weekly salaries. And a standard deviation of 45. Estimate the percentage of salaries. Okay, so we're trying to figure out what percentage of salaries lands here. We know that 907.33 is the mean. So I'm just going to go to the Desmos calculator. And 45 is the standard deviation. 907.33 is the mean. If I go 1 standard deviation up, I would add 45. Whoops, that's not an add. Plus 45. And I'm up to 952. Let me go see what the number was. It's higher. So let me add another 45 plus 45, 997.33. Let's go back here. So right now I know that 907.33 plus 2 times 45, or twice the standard deviation, is going to equal 997.33. 997.33. So this is going to match that. So now I'm going to try to do this with subtraction and see if I get the low value. Tab over. And I'm going to change this to subtraction to see if we get the low value, because this was 2 standard deviations above. So let me check the Desmos calculator. What if I do minus, that's not minus again, hit the wrong one. I'll just start all over, clear all. 907.33 minus 2 times 45 was the standard deviation. This is going to give me 2 standard deviations. 817.33. 817.33. 817.33. 817.33. Okay, so this number matches this number. This number matches, whoops, this number. So we are 2 standard deviations below the mean, 2 standard deviations above the mean. Where'd it go? The empirical rule states that 95% of the data values fall within 2 standard deviations from the mean. As you can see, both the low value and the high value are 2 standard deviations from the mean. Therefore, 95% of the salaries are between 817.33 and 997.33. So look at all the work that really needs to be shown for this question. Make that blue, and I want to make sure it's highlighted so you can see it. So here's the work right here. The empirical rule is where I got the answer from, and there we go. Okay. Estimate the percentage of salaries that are below. Interesting. So we know, according to the empirical rule, let's go back up here to that picture. So we're sitting right here at 2 standard deviations, right here, right? So from here to here is 90, here to here is 95%, right? So that means there's another 5% left over, which then is split between both sides. So we have the 100%, all of it, minus the 95%, plus the little bit down here. Let's see if we can follow that. Let me go back to this. It's a lot of stuff to think about in this question. So here's what we know. We know that 95% is in the middle. So 100 minus 95 leaves 5% left over. But half of the 5% is on the lower half. Half of the 5% is below the mean. So we have to do the 95% plus 2.5. That leaves us with 95% plus 2.5%, which will then equal 97.5%. Whoops, I forgot the 7. 97 97.5%. Okay. Approximately 97.5% of the salaries are below 997.33. So where did I start this question? Right here. So this is the actual answer. So I will change it to blue. This is the work to get to the answer. And then maybe I'll just highlight this so it really shows out. So we've gotten through the first 4 questions in every part. I hope you guys are feeling okay about this. All right. Oh, here's the empirical rule again. Let's see what it says. Suppose that the replacement time for washing machines are normally distributed with a mean of 9.3 years and a standard deviation of 1.1 year. So that means like basically the average person replaces their machine every 9 years, but it could be 9.3 minus 1.1. So that would be 8.2. That's one standard deviation below. And then above would be 10.4. That would give us 68% of the range. And then if you did 95%, you would be 2 below and 2 above, because it's saying empirical rule. Let me read the 2 questions now. Question A. I think I just answered them. 68% of the washer machines are replaced between. So what I need to do is I need to know what 9.3 minus 1.1 is. And hopefully you can see this. 3 take away 1 is 2. 9 take away 1 is 8. So it's 8.2 years on the low side. And now we're going to do the same thing, except we're going to add, change that to a plus, and 3 plus 1 is 4, 9 plus 1 is 10, so that gives us 10.4 years. I'm going to move this over a little so it ends up where the work is. So this is the work, and now it says answer the first blank here. 8.2 years. Second blank here, 10.4 years. Okay, so this is 1 standard deviation away from the mean, above and below. That's what the 68 means in the empirical rule. This says the washer machines for 95%. So I need twice of 1.1. 1.1 times 2 is 2.2. So I'm just going to take this same thing, be a little lazy, and change the 1.1 to 2.2. I'm going to change this to 2.2. I'm going to change this to 2.2. And you can see that 3 plus 2 is 5, right? And 9 plus 2 is 11. So we get 11.5. Oh, I'm supposed to be subtracting. Okay, 3 minus 2 is 1. 9 minus 2 is 7. That leaves us 7.1 year. Okay, now we add 5, 11.5, 11, and you can use the calculator if you want. 11.5 years. Oops, I need an S. And this one needs an S. So now I just have to write the 2 new years down. The low value is 7.1 years. The high value is 11.5 years. So what is this really telling us? People buy a washing machine, and 95% of the people who replace their washing machine replace it between 7 years and 11.5 years. This is saying that 95% of the washing machines are going to be replaced between 7.1 years and 11.5 years. The top one is saying 68% of the washing machines will be replaced between 8.2 years and 10.4 years. So that's what the average is going right now. Anything to make money, I guess. Okay, we're getting to the end almost. Okay, question 6. I had to get nosy. I did bring these two over. When I saw the Z here, I went to the top, to the notes, and I just copied and pasted the formula down at the bottom so that this would be a little bit shorter. Not that it really is shorter. Okay, the average height of adult females in Sri Lanka is 59.5 inches. That's just under 5 feet, with a standard deviation of 4 inches. The average height of adult females in Sweden is 65.5 inches. So that's 5 feet, 5.5 inches, with a standard deviation of 3.08. So I could see just from those sentences that the females in Sri Lanka seem to be, on average, shorter than the females in Sweden. I'll have to pay attention at the next Olympics. I did take this information from international statistics. I forgot. I should have labeled the name of the place where I got the information from. So suppose Tina is 68 inches tall. So they have 69 inches tall. I'm sorry, I can't even read. So she's 69 here and 69 here. Find the Z-score for Tina's height if she lives in Sri Lanka. Okay, so the statistic we're going to use is 69. So I'm just going to copy, Control C, move this over, and I'm going to paste in the values. The statistic for her is 69 inches. And the average in Sri Lanka is 59.5. So I'm going to back this up. Is 59.5 inches with a standard deviation of 4 inches. Whoops. Okay, so that's now filled in. Go out, get an equal. Before I do the calculations, I think I'm going to set the other one up too, because it's also 69 inches, but now it's saying she lives in Sweden. So the statistic is, whoops, I just want the statistic part. 69 inches. And the mean in Sweden is 65.5. 65.5 inches. Standard deviation is 3.08. They have a smaller standard deviation. Whoops. 3.08. And now I have everything. I just need to go to the Desmos calculator. Whoops, where'd that equal sign go? I don't know what I hit, so let me just hit undo, undo. I wanted the equal sign to go. Why is it going down there? I want it to be right next to it. There it is. Okay, so the first one, 69 minus 59.5. 69 minus 59.5. Clear all. I think I'm going to use a set of parentheses. 69 minus 59.5, that would be on the top, and that's going to get divided by the standard deviation of 4, and it's 2.375. 2.375. 2.375. Okay, and now it's 65.5 and 3.08. 65.5 and 3.08. So I'm going to do the same thing, use a set of parentheses. 69 minus 65.5 divided by 3.08. Let me just make sure I have those values right. 3.08, 65.5. Okay, so 1.34. Normally, unless they tell you differently, it's common to go 2 places or 3 places. So I could do 1.36, 1.136. 1.136. So it matches. But let's take a look before I even look here. To be in normal range means you are within 2 standard deviations. So when Tina is in Switzerland, she's normal height as everybody else. But when Tina is in Sri Lanka, she's a little bit taller, 2.376. She's just outside of the normal range. So she's mildly taller. She's considered unusually tall. It's only a little bit over. We would have to get into something called p-values. We do not do that in this course to really get the strength of evidence, but we have enough evidence to say she's more than 2 standard deviations above the mean, which means she's tall for people in Sri Lanka. Oh, okay. Identify which of the following statements is true about Tina's height. Tina would be considered unusually tall in Sri Lanka, yes, but not considered unusually tall in Sweden. That's true. Tina would be considered unusually tall in Sri Lanka, but not considered unusually tall in Sweden. Yes, that is true. Let's go to the next one. Tina would be considered unusually tall in Sweden. No, she's not, because she's not 2 standard deviations, so I'm done. Tina would be considered unusually tall in both Sri Lanka, and Sweden? No, because she's over 2 standard deviations in Sri Lanka. Tina would not be considered unusually tall in either country. No, that's not true because in Sri Lanka she's unusually tall. So there's only one true statement there. Okay, let's look at the next one. Fill in the blanks. Out of 140 adults sampled, 98 said they have checking accounts. As soon as I see that, 140 sampled, 98 have checking accounts. First thing I'm doing is this. 98 divided by 140. That's going to give me the sample statistic. And there it is. It's 0.7 or 70%. Let me go back to reading. Okay. The percentage of people in this sample who have checking accounts is called the sample statistic. I already know it's 70% because I just went and looked it up. As soon as I see something like, that, I tend to write it right away. Okay. It just asks for the number. It didn't say anything else, so that's all I have to give is a 70%. Okay. The researchers conclude that they are 95% confident that the population, the true percentage of adults who have checking accounts, is 68 and 78. It should say between. I think this is missing a word. I'm just going to add the word between. If it's not on yours, you can add it. Is between 68 and 78. Use this information to answer the following questions. So they're saying 95% of adults are between 68 and 78. And I can almost see the smack right in the middle of those two numbers right now, because 68 to 78 is a spread of 10, which means the margin of error has to be 5. But I'll prove it to you. The margin of error has to be 5%, but I will prove it to you. Oops, I didn't need that part with it. I'll prove that to you in a second. Oops, too far. Just want the 5. Oh, I don't need the percent here if I have the percent there, because I'm putting a percent and a percent. The percent is already on the line. So the 5. Okay, so there we are. Boy, this is really easy. I don't even have to do any real math. The confidence interval can be written as, well, let me just prove the other thing. 68 minus 78 divided by 2. So this is going to be, the higher was 78 minus the lower, which was 68. And there's only 2. So to get the margin of error, you only want half the width, which is 5. I just wanted to prove it to you. So we start with the statistic, which is 70%. So in here would be the 70 plus or minus. Here would be the 5. So this would be 70% plus or minus 5%. I don't like the way this question is. I did it the same way. I just copied and pasted from the quiz form over to make it match. So I would prefer to write this myself. If I were writing it, I would do 70% plus or minus I actually like this way of writing it better, but it doesn't make a difference. So there's the whole quiz. So I really hope that you take the time to go through this review, study the notes. You cannot take this quiz on any day other than the day that it was assigned because it needs to be done during finals week. Bye. I hope you find this helpful. I have really enjoyed working with you guys. Take care. Stay well. Happy holidays.